So welcome to the third lecture of digital system design with PLDs and FPGAs. The last class we had a brief revision of the basic subjects. So let us quickly run through those slides before today's lecture. So let us move on. Essentially we talked about the major constituents of the digital design. To start with, we will look at the function, and there are two parts. One is a combination logic, higher level blocks we said, all those blocks which you have studied in the basic course. Then we have the sequential elements like flip flops, registers, memories and all that. This constitute the function part which you have to learn thoroughly, and we have looked at the minimization using some algorithms, single output minimization like Karnoff maps, Cohen-Mikulski, Espresso, and for there are multiple output multi-level minimization which is based on this algorithm, but then it involves many other steps. We had a brief look at it. Then we looked at differentiating between the gates and the functions the gates are able to implement. Then we had basically it is bringing the De Morgan's theorem into our concept, and we have seen that the NAND and NOR are universal gate, and we have seen some example of AND OR is getting implemented using NAND gates, and also we have seen how advantageous is to conceptually think like that. Then you will not waste gates if you bring this into concept while designing some simple logic circuits. And we have looked at the encoder, the decoder, the multiplexers, the tri-state gates, and we have seen what is a tri-state gate and some care need to be taken when you are busing or multiplexing using the tri-state gate. You have to pull up or pull down. Then we have looked at the multiplexer and demultiplexer, and real life that it may not be like a textbook picture. Then we have looked at the difference between latch and a flip flop. Latch is transparent, flip flop is edge triggered. We have looked at the timing, that is a second important constituent of the design, and for a combination circuit what is the timing? It is a propagation delay, and for sequential circuit flip flop there is a propagation delay called TCO, and at the input you have to meet some time called setup and hold time for the flip flop to transfer the input to the output properly. Then we have looked at something called hazards, where in unexpected outputs you will get glitches, which I said there is static 0 hazard and static 1 hazard. In a sequential circuit is not a problem because we latch the output after settling. But this is just a model. In real life whenever there is an unbalanced path delay at the input of an AND gate or an OR gate, these glitches can happen. So one has to wait for it to settle before latching onto a flip flop or a register. You can have dynamic hazard for a single change in the input. There could be multiple glitches at the output instead of one pulses. Then you have electrical characteristics, basically voltages and current. We have seen output voltage, output currents, how it is the voltage is related to the current. Then we have seen the noise margin, the fan out, how to calculate the fan out, the power dissipation for a switching power dissipation, or the leakage power dissipation, expression for the power dissipation in a CMOS output stage. So that is where we have dissipation of the whole circuit. So we can attack at a lower level, at the transistor level, the power dissipation. At the circuit level we can reduce the power dissipation. The third level is that when you have a system, complete embedded system, say with a processor with lot of peripherals and all that, and a particular circuit, particular system may not use all the peripheral at the same time. So it is possible to power down the the peripherals or the modules which are not working, or you can freeze the clock of some registers or memory so that it reduces the power dissipation, or you can reduce the clock frequency of the unused blocks so that the power can be brought down. It does not stop there. Maybe when you are designing the whole architecture, you can take care that the architecture is designed such a way that the power dissipation in the system is reduced. So that can be handled at the architecture level. Ultimately, one might think it stops here, but it does not stop there. When you choose the algorithm for some computation, you can choose an algorithm which reduces the power dissipation. There could be, like you have a multiplication, there are different algorithms you can use for multiplication, but there may be algorithms which reduces the power dissipation, but it may be slow. But if our primary aim is to reduce the power dissipation, then you can choose an algorithm which reduces the power dissipation. So the low power design can attack at all these fronts, these transistor level, circuit level, the system level, architecture level, and at algorithmic level the power can be reduced. And this is a very major focus in the current VLSI design. Even in devices like FPGA, one would like to have low power dissipation, but this is not the focus of our course. So I will I have given a taste of it, and if you want low power to know about low power VLSI design, you have to go and credit a course which talks about it, or read a book in the low power design domain. So let us move on. What is the next issue in design? So that is a high frequency design. You know that in high frequency the tracks or the lines or the wires within on a PCB or a chip can act like transmission lines. So there could be reflections. So unless we take care, maybe your logic is correct, the timing is correct, everything else is taken care, but because of the high frequency the wires can act like transmission line. If there is impedance matching problem, there can be reflections which can corrupt the signals. So this has to be taken care in high frequency design. Similarly, there can be crosstalk, like when you have two wires running parallel for a long distance, then one signal in the wire can be coupled to the next signal. So you can imagine what can happen if the clock line is running close to the interrupt line of a processor, then that is disaster. So this has to be taken care, the crosstalk. Similarly, there is in the noise analysis, there are ground loops, the ground currents, say there is an analog component and there is a digital component in the chip. The switching current of the ground can pass through the digital ground can pass through the analog, that can create problem in the analog circuit. All these has to be taken care, and that is done in the backend tool. In the backend design there are special tools for it, and this is also an important area one need to know in VLSI. So let us move on to the next technology, that is the device technology. So our course is about PLDs and FPGAs. So it is let us have a look at what are the device technology available. One thing is the application specific integrated circuit or ASIC, and this is normally supposed to be full custom. So that means it is designed from scratch, almost everything is designed at the gate or flip flop level. Maybe they will use some library cell, but most of it is designed from the scratch. The problem is that it has a very huge cost, because one has to set up the EDA tools for design tools for it, people have to work on it, and the foundry has to set up, and the chip has to be fabricated. So it has a huge non-recurring engineering cost. That means it is a one-time cost is huge, and that has to be amortized over the number of the chips produced. So if the chip is produced only 10,000, you cannot possibly make an ASIC and get money out of it, because each chip will cost so high. So the ASICs are designed only where there is high volume, like you have the desktop CPU or the mobile phone SoC chips and so on. So, and this also take a large turnaround time from the finalization of specification to the first chip. It may take 1 year, 1.5 years, 2 years and so on. So this ASIC is a huge costly affair, but once it is designed it can be made to work at very high frequency, like you have 3 gigahertz processor chips. That is because it is ASIC, it is custom design. Many a times people do not have such luxury, they do not have the number to justify such a cost. Then one can go for semi custom design, that is a mask programmable or standard cell. That means that the foundry will give you some standard design and you make your system based on that standard design, and the foundry has all the layout for those blocks. So it is quick when you send out the interconnection of the standard cell or the array of gates, it is quickly interconnected at the foundry. So this works for the medium volume, it has medium NRE cost, medium turnaround time. The field programmable gate array. So this is the device technology. So the next I want to touch on the current state of the VLSI technology. You must have learned that the PMOS is slower than the NMOS, because the hole mobility in PMOS is less than the electron mobility in NMOS. But you know that with the current technology like strained silicon, the PMOS is getting faster. Strained silicon means the silicon lattice structure is strained by some deposit on top of silicon. So the lattice structure kind of stretches so that the electrons and the holes can pass faster. So the PMOS is getting faster, and the current feature size is the technology wise is 22 nanometer, and if you look at the Intel Core i3, Core i5, Core i7 is fabricated in this 22 nanometer, and the next technology which is coming, which people are working, the manufacturers are working, is 14 nanometer, where the inverter delay is of the order of 5 to 7 picosecond. So you know how fast this technology is going to be. But now the present trend is not to make things faster. You know that we are reaching the limit. So one can't expect this to go down considerably in the same scale as before, but people are using parallel multiple core for computation. You know that the Intel current chips has the quad core and 8 cores and things like that. The present trend is not on the raw speed, but to have multiple computational units parallelly working whenever possible. Okay. So which is many a times possible because there are in a processor or even in a mobile phone there is multitasking. So it will be good if you can listen to the music on a cell phone at the same time you are going for a walk and you want to capture the picture. So if both can work parallelly, it is very good. It is very bad you are listening to music, then you click a picture, if the music stops, yes, nothing catastrophic happens, but the user experience might get interrupted. So I am not greatly talking about the social implication of the technology, but the good things can happen with the multiple core parallel computing and things like that. So let us move on. Next is the design methodology. We will have a look at it. We have already touched upon it, but then let us have a look at the design methodology of the VLSI and FPGA. So as I said, there is something called front end design, and which goes basically from specification to the gate and flip flop level circuit or the netlist, or we can say from algorithm we design an architecture and we go to the logic circuit in terms of the gates and the flip flops, and this is many times called logic synthesis. This step of going from an architecture to the logic level circuit is called logic level synthesis. Then the moment you have it, the circuit here, that the front end design is over, then we go for the back end design. In the back end design this gate and flip flop level netlist is converted to the chip mask, not in one step. First the logic circuit is converted to the transistor level circuit, and this is called physical synthesis. That is the physical transistors are synthesized out of the logic circuit, and thereafter each transistor and the interconnection is designed in detail in terms of the mask which is required for the fabrication. So that is a back end design as far as the VLSI integrated circuits are concerned. But if you take the FPGA, we do not go for this step. The FPGA has already the logic circuit built in as logic resources with the wires laid out with switches in between. So you literally go in one step from the logic circuit to the configuring the FPGA. So for FPGA this physical synthesis and chip mask is not there. We directly go from this circuit level to the configuration of the FPGA directly, with of course there is a step involved in translating this circuit, mapping it to the resources of FPGA, interconnecting it and so on. So that is a back end design for FPGA. So we talked about the front end design and the back end design. So let us continue. As I said, in a digital design there is a data path where the computation happens. It is made of registers and combination circuit, registers holding the value, combination circuit computing it, and there are controllers or finite state machine which control the data movement in the data path. There could be multiple controllers or a single controller depending on the need. And in VLSI design we have metric or we have constraints. These are the constraints, the area. Normally one would like to have a smaller area so that the chip is smaller, you can make more chips and reduce the cost, and when the chip is small it will be compact and the delay will be less, the wire delays will be less and the power dissipation will be less. So these are conflicting requirement. It is not that you can have small area, small delay and small power. So where one go for small area, some block you may get a larger delay, and when you go for a very fast circuit you may end up with a large area and a large power dissipation. And if you have looked at even a very simple example like an adder, say you have studied ripple adder, you know that suppose we have an 8-bit ripple adder, it uses 8 full adders cascaded. So the area is very less. You know what is in a full adder. Full adder use 2 exclusive OR gate and 3 AND gates and an OR gate, okay, at the maximum. So such 8 stages, but it is, you know that it ripples through 8 stages. In the worst case, if one stage delay is say 1 nanosecond, the worst case delay of addition will be 8 nanosecond. But you can go for a carry lookup adder which has only 2 step delay. So anything you add you will get in 2 steps, maybe 2 nanosecond. But you know that when you go to, as you go from the 0th bit to the 7th bit, the whole circuit gets exponentially larger and larger and it occupies a lot of area. The carry lookup adder is not very seriously used because of this problem. It occupies huge area. So just an example saying that these are conflicting requirements. You do not get everything low, it is very difficult. You have to make a trade off between the area and delay. So let us move on. So the next thing I want to talk is this thing called system on chip, which is or SoC, and many a times you have a word called intellectual property or IP. So you know that earlier, maybe 10 years back, a system was designed on number of boards. You have a box or you have a rack based system where there are multiple boards. Like earlier if you looked at the computers, there are motherboards, there are daughter boards, but now it is shrunk to a single motherboard, everything is built on the board. And if you look nowadays onto the motherboard, there are very few chips. You have a processor chip and a peripheral chip which is also getting kind of integrated into a single chip. So The complete system of the desktop CPU can go as a single chip. Maybe the DRAMs, DDR3 memories will be outside, but things are shrinking. So the complete system will be on a chip. It will reduce the power dissipation, it will reduce the area, the cost will be reduced, the delays will be less, and the power dissipation will be less. And same thing is happening in the FPGA domain also. In the ASIC domain you have system on board, in the FPGA domain you have programmable system on chip. Okay, that means you have in the FPGA domain also you have lot of processors, peripherals are built into FPGA, and you design your custom design on the FPGA, put it together for a system which is called programmable system on chip, and some manufacturers call system on programmable chip and so on. Okay, so if you take a system on chip, it has lot of things typical. I am taking an example. It may have one or more processor cores, so it will have a communication. Maybe there is a processor for basic communication, there is a processor for control, there is some DSP for computation, there could be multiple cores of DSP or control processors and so on. There are a lot of peripheral devices like memory controller, UART, USB, the timer and so on, IOs and so on. There will be one on chip bus architecture because a lot of peripherals need to be interconnected. So there will be some kind of bus architecture on the chip, like if you have an ARM, you have an AXI bus in an ARM based system. Maybe like on a PC you have the PC chips, they have the local bus within for connecting the memories, and you have network interfaces. Maybe you have Ethernet interface or a Wi-Fi interface and Bluetooth interface and so on. Then there could be custom hardware for packet processing, signal processing like codec. You have a TV set-top box which has an H.264 or MBEC4 decoder that is required, and ultimately you have the software, the real-time OS or the OS, the network protocol stack, application software, everything in a flash memory in the chip, within the chip. So that is an SoC. So don't get, if you don't know what is system on chip, a typical system on chip is like this. And let us move on to the next keyword, which is many times called intellectual property, which is related to, somewhat related to system on chip, because when you have a complete embedded system, it is very difficult to design from the scratch. And you know that the way the short time duration in which the cell phones are coming into the market with newer and newer chips, and it is very difficult to design a complete system in 6 months. So most manufacturers, when they design a system on chip, they use already designed components of CPUs, of peripherals, of codecs and so on, and they buy it from somebody who have already designed it and just put it together for as they require. So that is called intellectual property. This designs which is already done is called the intellectual property. There are different type of soft intellectual property. One is a soft IP. Soft IP would mean suppose you have a memory controller, VHDL or Verilog you can buy and use it. It is very flexible because you can change it depending on the license, but then you have to synthesize it. You have to do the front end design, the back end design. Maybe it may not be depending on your tool and your the way you design, it may not end up in an optimized design, and it may not give the desired delays, it can be slow. So soft IP is very flexible, but it may not give the performance. The next is a firm IP, which is nothing but a synthesized IP. That means the logic circuit is synthesized. So it may be optimally synthesized with a minimal logic circuit. So it can work faster, but the changes are difficult now, because earlier it was a hardware description language, you could easily change the design. Now you have to change in the synthesized design in terms of the gates and flip flops. It is cumbersome. It is a better option than soft IP in terms of performance, but flexibility is less. The last category is a hard IP, where this is literally not the synthesized circuit, literally place and routed IP. So you can directly place it in the silicon. The silicon the mask is ready for that circuit. So you integrate this hard IP with the other hard IP at the back end tool level. So the advantage with this hard IP is it is already tightly integrated, very optimally placed and routed. So it can be very fast, but you know that any change in this hard IP is very difficult because it is already kind of physical synthesis is over, the transistors are over, chip masks are ready. To change it is quite tough. So these are the IPs, but the present the design trend goes for the IP design, and people make IPs and sell it to other people. You know the ARM chip, the ARM processor, this is an IP, this is not a chip, mostly you buy from the manufacturers. The ARM consortium give it to whoever wants it, they license it, and they ask for some royalty, and people are very happy with it because there are a lot of peripherals, and the processor along with the peripherals can be integrated, and there are a lot of standard IPs available, standard OS available for ARM processor. So let us move on. This is the next technology, that is something called dynamic or runtime reconfiguration, which is very much talked about, researched pretty much. So this can work in FPGA and as ASIC level, and the basic idea is that a part of a device is reprogrammed to implement a different functionality. That means take an example, say you have a SoC which is used in a mobile phone, and suppose you are working with Bluetooth, okay, then that Bluetooth part of the hardware is programmed into the chip, okay. Now suppose after some time, instead of Bluetooth you are connected to the Wi-Fi, okay, the wireless network, not the Bluetooth, and you are not using the Bluetooth at the same time. Then what is done is that at the runtime dynamically this Bluetooth part of the hardware is removed and the Wi-Fi part of the hardware is put. So you can save a lot of area and reduce the power dissipation and the cost and things like that. This can happen, this is supported in FPGA, but you can even do this cleverly in ASIC, which saves area, which allows reconfiguration. Maybe you can even think of a system level reconfiguration, like you have a general purpose device maybe which can act as a cell phone, after some time it can act as a general computing device like a tab or a pad like that. So it is quite advantageous. Here the important thing is that the reconfiguration time is important. You should be able to reconfigure very fast. Suppose you turned off the Bluetooth and you switched on the Wi-Fi, then if it takes some 10 seconds for the hardware reconfiguration, then this may not satisfy the user. So the reconfiguration has to be faster, and very important is the granularity is important. What part of the circuit can be reprogrammed is very important. Suppose the manufacturers restrict saying that only half the part of the chip can be reconfigured and all of the half part has to be reconfigured and things like that. The granularity is important, and the flexibility, how flexible it is, like we should be able to reprogram any part of the chip or any area of the chip flexibly. So this dynamic reconfiguration, this granularity, the reconfiguration time, the flexibility is very important. So let us move on. This is another area as embedded system is concerned, like also when system on chip is considered at a top level, you need something called system modeling. When you start with a system on chip, you are not sure what part should be in hardware and what part should be in software. So there many a times you know that the hardware design is done in HTL and software design is done in C or C++, and it is a very cumbersome thing to like once a partition is made, the hardware designers start designing the hardware, and the software designer start designing in software, and half the way you realize some software part has to be moved to the hardware. It is a very tough thing. So it will be good at a system level you can model and study the performance and the costs. That means hardware you know that it is concurrent, we can make it very fast, but it is very less flexible and the cost is higher. But software is sequential, it has a lower performance compared to the hardware, but it is more flexible. You want to change the software, you can change it easily. So it will be good to have a system modeling language, we can model it together in one language and work out on the cost performance trade off and freeze it, then go for the hardware design and software design after partitioning. So the languages like System C allow the system modeling, and there is a system Verilog language which is mainly used for the system verification. So that is all about the system modeling. Let us move on. You have learned like suppose you have learned the VLSI design or FPGA design, that in itself is not an end, because if you know how to design a VLSI chip or an FPGA chip, but it is of no use, but you know that you have to design the chip in some area. So it is very important to know that where these chips are used, in which domain it is used. Okay. So maximum the ASICs or FPGAs are used in communication networks. So if you are an VLSI or FPGA designer, you should have some background in communication networks. So let us turn to the communication network. So you have learned about the layering of the protocol stack. Say layer 0 is a physical layer, layer 1 is a data link layer, layer 2 is the layer 1 is the physical layer, layer 2 is the data link layer, layer 3 is the network layer, and so on. So if you take the physical layer, mostly it is analog and digital mix. If you take the data link layer, or many a times it is called MAC layer or media access control layer, it is digital mostly, and in the case of a computer it is in hardware, but it is controlled by a network driver. The operating system will have a driver to control this data link layer. So whenever a new networking protocol comes, like you have the Wi-Fi or you have the latest protocol stack, then a lot of design has to happen in the data link layer to implement this in a chip. And similarly network layer, there is a layer 3 where the packets are switched or routed, and that is, as far as the end systems are concerned, it is done in software. But if you look at the routers and switches on the main network, this will be done in hardware. So there is a lot of hardware work within the communication network. So it is worthwhile for a VLSI or FPGA designer to learn about communication network, communication protocols, because a lot of communication network based chips are designed. Similarly, a lot of things are happening in the signal processing, like multimedia, the video encoding, video decoding, H.264, MBEC4, and various other codecs need to be designed, filters need to be designed, a lot of compression need to be done. All this happen in the signal processing area. So for an VLSI or FPGA designer, it is very important to have some basic background, the algorithms of signal processing, so that you can implement it. And ultimately computer architecture within the like designing a CPU, that is a job of a VLSI designer. Many times it is prototyped in the FPGA, then move on to ASIC domain. So your FPGA design can move ultimately to the ASIC design. So the computer architecture, so 3 areas, one is a communication network or computer networks, then signal processing, computer architecture. So that you should learn the basics of it, so that when you design for a particular domain, this knowledge comes handy and you will be a good designer in the field. So better know this. So that gives an overview of the field. So we started talking about the various issues like application areas, design methodology, device technology, then the system modeling, then the high frequency design, low power design, and so on, just to give a glimpse of the state of the art or the current technology to be aware before moving into the nitty-gritty of the digital design. So we have some time left, so let us move on to the digital design. So let me put the slide. So I call it advanced digital design. So in this advanced digital design we will conceptually develop from a lower level to the higher level. We will start with small system, then build. We will see how the bigger systems are built upon these basic building blocks, and what are the standard basic building blocks to understand the structure, timing and so on. Okay. So let us move on. The first thing, let us take the synchronous sequential circuit. Okay. So that is the first thing. So I assume, as I said before, I assume all the background that you have learned the combination circuit, sequential circuit, and now we are coming to the serious design, sequential circuit and synchronous sequential circuit, and we will learn 3 things essentially: the structure of a synchronous sequential circuit, what is the architecture of it, how to design it, say knowing the structure, how to design it, and do the timing analysis of the synchronous sequential circuit. So that is what is shown in the slide. So we will study the structure of a synchronous sequential circuit, design of it and the timing analysis of it. And you must have learned, we will start with the basic very simple thing you have learned, that is the synchronous counter. You must have learned in your undergraduate program something called a ripple counter. Okay. This is a very crude circuit which has less use. So like you have a suppose in a ripple counter you have the least significant bit, the output of which will clock the next bit and so on. Okay. This is not timing wise not a very good circuit. So forget about the ripple counter, let us take the synchronous counter. Synchronous counter is the simplest synchronous sequential circuit we can study, and the structure is same for all the synchronous sequential circuit, or at least we can build on the basic synchronous counter. So let us try to design a very simple counter. So let me ask you how to design a modulo 6 counter. Okay. So modulo 6 counter has 6 states or 6 count which start with 0. It is a binary counter which start with 0, then it counts 1, 2, 3, 4, 5 and then goes to 0. Okay. And then it continues, it loops. Okay. That is a mode 6 counter. So how to design this counter? Okay. So let us go step by step. So we use binary encoding, so that means we will encode the 6 in flip flops. So we need logarithms to the base 2 number of flip flops, which comes some 3 point some number, so 2 point some number, so we have to use 3 flip flops. So let me put 3 flip flops. Okay. Now I am already abstracting. In your basic course you would have already put 3 flip flops separate and try to design. So the first thing to notice is that we cannot go to the complex system with separate flip flops, because if you try to design something 32 bit, we cannot put 32 flip flops and in a paper or anywhere and design. And we are also not we are also not going to detail gate level design, we are going to use the higher level blocks. So we do not need to know all the details which is done by the tool, optimization is done by the tool. So we go to a higher level. So I have put 3 flip flops together, and you can see there is clocks are tied together. In a synchronous circuit all the clocks of the flip flops are same. So you get a single clock is connected to all 3 flip flops. A reset is connected to all the asynchronous reset. Now there are 3 Qs, Q2, Q1, Q0 and 3 Ds, D2, D1, D0. Okay. Now assume that at the power on we have power on this, at the power on this has become 0, 0, 0, 3 zeros, that means the value is 0. Now when the clock comes we should get the 1 here, okay. So that is the basic counter design. So how to make it 1, okay. So we have initially made the 0 and somehow we have to derive in the next clock we have to get the 1, and you know that when the clock comes whatever as far as the flip flops or registers are concerned, whatever is here is transferred to the queue. So it is worthwhile, it is enough if you have 1 ready here. So when the clock comes 1 comes here, and in the next clock 2 should be ready here. So you get the idea, you at the beginning you have 0 here, but we want 1 at the input. So it is enough if we put a combination circuit here and feedback the present count to the input of that circuit, so that then we design that circuit such that given 0 that will give 1, given 1 that will give 2 and so on, okay. So what I am saying is that we will put a combination circuit before the flip flop and the input of that is the output of the flip flops, and the output of that combination circuit goes to the input of the flip flops, okay. The basic idea is that we design this combination circuit such that given 0 it gives 1, given 1 it gives 2 and so on, okay, in this fashion. Then when the clock comes initially it was 0, in the next clock the 1 comes here and that 1 gives 2 here, next clock 2 comes here and 2 comes here and so on, okay. So you design this circuit, then you get a counter which count sequentially 0, 1, 2, 3, 4, 5, and you must have learned again in the basic course something like you want a mode 6 counter, you have a mode 8 counter, and then what you do is that which counts up to 8, but then you catch 6 here, decode and reset it, and then it becomes 0 and so on. But there is a problem, if you reset it using an asynchronous reset for a brief duration it might go to the next state and so on, okay. Like you wait for the 7 to come here, then you reset it, then 7 there is a glitch 7 at the output, but this is a very neat design, it works perfectly. But next question is, so that is the structure of a synchronous counter. You have flip flops and many a times we call this as a present state of the flip flop, and it goes to a combination circuit, and the output of the combination circuit is called next state because upon the clock the next state become present, that is why it is called next state. And this combination circuit is even often called next state logic because it's a logic, it's a combination circuit which decode the next state from the present state. Now it is very easy to design, we have to design, basically we have to design this combination circuit, and we know how to design a combination circuit. Write the truth table in terms of the input, present state is the input and the next state. So you write the truth table. So we take this combination circuit, develop the truth table, the present state has 3 inputs Q2, Q1, Q0, and the next state as we call it, let us call it D2, D1, D0 because it is going to the D2, D1, D0. So the moment you know that, you write the truth table, we have to look at the D2 separate, D1 separate and D0 separate. In the normal course of time you would have picked all the ones in this D2 column and go to the Karnaugh map, minimize it, and you come out with an equation or a sum of product equation in terms of Q2, Q1, Q0. So ultimately you will get 3 Boolean equation in terms of D2, D1 and D0. So let us write that. I say Di is Fi of Q2, Q1, Q0. So I is nothing but 2, 1 and 0. So you have D2 is F2 of Q2, Q1, Q0, D1 is F1 of Q2, Q1, Q0, D0 is F0 of Q2, Q1, Q0. So you get 3 equations that can be implemented. So normally we are not going to do this hand level design, it is enough if you describe the truth table in terms of the hardware description language in a high level design, then you get the design, okay. So many a times this is also called the next state is a function of the present state. So we call it next state is a function of the present state. So mind you, the next question I want to ask is that we still take the mod 6 counter, but it does not count sequentially like 0, 1, 2, 3, 4, 5, 0. It counts in a crazy way that it starts with 0, then 5, 3, 2, 1, 4, 5. Okay. So the question is, can we design such a counter? You know already the answer is very simple, absolutely no worry. Anybody specify anything, you change this next state logic, you change the truth table, you write start with 0, the next state is 5, you write 5 here, the next state is 3, you write 3 here, the next state is 2, and so on. Then you form the equation or write the truth table in VHDL code. Then this should be perfectly okay, it can be designed. And so let us look at a little bit timing, how this present state changes with respect to the clock, to give you an idea. You may already know it, but then let us look at the timing, the symbol timing of a counter. So let us move on. So here this is the clock waveform, you have the clock edge, and this is a positive clock edge triggered flip flop. So at the positive clock edge, the present state changes its state, and that cannot happen immediately. In many times in textbook it will be shown that this state change will coincide with this active clock edge. In practical circuit with delays it does not happen. You know that here the flip flop has delay called TCO. When the clock comes, this D is transferred to Q with a delay called TCO. So after the clock edge it takes TCO time for the present state to change. So when the clock edge comes, the state will change, the count will change only after the TCO. So similarly here it is 1, then but when the clock edge comes, after a TCO delay it changes to 2, and after TCO delay it changes to 3, and so on. Mind you, there are 3 flip flops, so there is Q2, Q1, Q0. So there is TCO1, TCO0, TCO2. So I am showing only one time. So there are 3 TCOs, we are showing the worst case timing delay. Okay. So this is one disadvantage when you go for little abstract high level block diagrams. It hides lot of details. Actually you are used to maybe showing the 3 flip flops separate in thinking that clarity comes, but you should be very careful when you put higher and higher level blocks, more and more abstract, you should not forget the details involved. So here you should know that when you say TCO, it is 3 TCOs, we take the maximum. For the maximum, like 3 outputs are changing, we wait for the latest output to settle. There will be lot of glitches here. I am showing just a state change, but there can be glitches depending on the state change, say like from 1 to 2 there could be glitches, okay, because there are 2 bits are changing, like 1 is 0 1 and 2 is 1 0. So there are Q0 and Q1 is changing state, there could be transitory state in between. So there could be glitches which I am not showing here, but this in real life it can happen. So let us look at a picture of a binary counter. I just want to show that picture. Okay. So this is a real picture, this is what you have used. I am showing a mod 8 counter which is count from 0 to 7. So you know that this is the picture we have shown in an abstract next level higher level block diagram, but here you see D0 is Q0 bar, D1 is Q1 exclusive or Q0, and D2 is Q2 exclusive or Q1 and Q0 and so on. Okay. So when we put it, you should not forget that D0 is a function of Q2, Q1, Q0, D1 is a function of Q2, Q1, Q0 and so on. In the case of a binary counter, you know that the Q2 only D2 only depends on you know the Q2, Q1, Q0, and D1 only depends on the Q1 and Q0, it does not depend on Q2. But if you take a a counter which count not very sequentially, all this can change. Maybe the D0 can depend on Q2 also. So that is just to say that don't forget when we use such block diagram, don't forget the detailed picture you should have in your head, you should in the mind, otherwise you can make mistake in analysis. When you analyze some circuit or debug some circuit, you can forget something and make a it can create trouble. So we have looked at the basically at the structure of a synchronous counter. How what is the structure? It consists of flip flop and combination circuit, and the flip flop output is called present state and combination circuit is called next state logic. It's basically designing the next state logic. All the intelligence is in the combination circuit. The flip flops are used to control it, hold the value at every clock. This looks like this is like a gate which allows gate is open, then the next count comes in at the precise interval, it's precisely controlled, every clock edge the count changes. And then we have looked at the output waveform. So in real life the output changes after the TCO delay, which is the worst case delay of the multiple TCO of the output. And finally I have told about you should, though we abstract to the next level of the diagram, you should not lose sight of the detailed diagram, because if you forget it then you can make mistake in analysis, in understanding and so on. So I stop here. In the next lecture we will continue with the timing analysis of this, and we will build on this. We will go on to the real life design, system level design very soon. So I suggest you go back to this lecture, revise, do some simple design of the counters, look at the structure of it, try to understand the timing details and so on. I wish you all the best and thank you.